All right, welcome to MAE 242, Fluid Mechanics, Recitation 5. So, like I was saying, this is a really important recitation. It's over all sorts of control volume analysis things. This is pretty much the basis of your entire exam too. So it would benefit you to pay attention a little more today. But, all right, so I'll write down the governing equations that we're going to be using pretty much all today. And they are the conservation of mass equation, which I guess you guys learned this morning. And for the scope, like moving forward, whenever I denote volume, I'll put a V with a line through it, and then for velocity, it'll just be normal V. Yeah, don't worry. I would do like a squiggly V, and that's stupid. I don't know, people do that. And that V with the arrow, that means it's a vector. So we're gonna, when we go and break stuff down, you know, you dot it with a normal vector so that if you have like an inlet flow, dot it with a normal vector, it's a negative sign and things like that. So that's conservation mass equation. Basically what comes in has to go out. That's why everything equals 0. And these are all in terms of like kilograms per second, you know, mass flow rate is what we call it. Or, you know, slubs per second, whatever. And then conservation of momentum. And this is historically the more tricky of the two. We have some of the external forces equals same time derivative term. So you have some of the external forces equals that same time derivative term plus your momentum flux term, and then there's also pressure force term. And some professors will have different sign conventions on this stuff. Don't be freaked out by it. Whatever your professor tells you to do, use that sign convention. There's a billion ways to do this depending on how you look at everything. But important thing to note is translational momentum is very much a component-wise thing, which you'll see in question 2 that we do. Depends on the angles of everything. I guess so is conservation of mass. We don't usually ask you questions about conservation of mass in a like vector, super angular oriented way, but conservation of momentum definitely. So that's why that one's a little more tricky, because people will forget about like the y component of something, or they'll just forget to take, yeah.
Is there a reason why there's a velocity component in that first time derivative of conservation momentum?
That's just how the math works out. There's technically, my aircraft prop professor explained it like in a really succinct way, and I was thinking about like writing it down but it's, if you look back, it's that like everything has to end up equaling units of force, and like that's how it ends up being units of force. There's a very mathematical physics way of explaining it that as an undergrad kid, I don't really know off the dome, but just for now, don't care too much about the derivation of it. That's just what it is. But anyway, all right. So that's our base equations. Let's get into it. So question 1, there are 2 water tanks, A and B, separated by a vertical wall with a hole in, with a hole. Okay, yeah, this whole PDF got all messed up when it was getting exported out. So first off, this is like 5 cubic feet per second, and then yeah, this is like 0.2, and that's like 0.05, whatever. But all right, so you've got some fluid coming in here, coming into this tank, fluid coming through this hole, coming into this tank, and then fluid coming out of here, out of that tank. And these are the heights of the tank, respectively. So first off, step 0 of all of this stuff is first off, dry yard control volumes, okay? And so for this one, we'll have two. We'll have one for the first tank. We'll go like that. And you usually get 3 points just for drawing a control volume on your exam, so do yourself a solid and draw a control volume. Okay, there's that. And then also we have to state our assumptions very clearly, because a lot of these problems you just can't solve without assumptions. So first off, I'm gonna say it's inviscid. There's no friction force. Let's see, what else can we say? Unfortunately, we have to say it's not steady, because we say, in part A, we have this H1 that's changing over time, and since the volume is changing, this term over here, this dV term with respect to T, that has some sort of rate of change with respect to time. So that time derivative term, we call that the unsteady term. You'll see me write that on some of your homework keys. I'll say unsteady term equals blah, blah, blah. So that's what that is. And if it was steady, we could say that equals 0, but we can't say that. So I have to say not steady or unsteady. And so does not equal 0. Let's see, we have 1D fluxes though. And basically that just means that your m dot equals your rho VA. Let's see, what else did I say? It's pretty much the big ones. Yeah, I didn't really write anymore. Yeah, that's all the really big ones. Anything else I didn't think of? Oh, incompressible, of course, that's. So that just means that density is constant. All right, now, that should be all we have to do. So, all right, let's get moving. So, for part A, I'm gonna find the rate of change of H1 over time, all right? So, we're gonna do our conservation of mass, and I'm not gonna rewrite it. I'm going to simplify it over here. And so I'm gonna say, so we're gonna have 0 equals, oh, and I'll also say, before I do anything, before I get ahead of myself, m dot equals rho VA for these assumptions, which also equals rho times q dot, because q dot equals v times a. That's why you have like cubic feet per second, because that's v times a. So we're conservation of mass. So we have 0 equals this, I'm gonna call that unsteady term, I'm gonna call that its own like m dot, all right? Or its own q dot, I'll call it rho q dot for its own unsteady term, all right? And now, since this inlet flow, let's mark our normal vectors. It's coming out like that, and then this one's coming out like that. The way we define it, it's coming out like that. Cool. So, technically speaking, for the second control volume, depending on how you define it, for this first part, we're calling that normal vector out that way. So, yeah, so for this first inlet flow, since we have the flow going directly against the normal vector, totally separate directions, that one's negative. So minus rho q dot in, and opposite for the other one, plus rho q dot out. So we simplify this, and we get rho q dot equals rho q dot in minus rho q dot out. Obviously cancel out the rows. So we get q equals 5 minus 4, because that's what we're given. Q1 is 5, Q3 is 4. So we get q dot equals 1 cubic foot per second. So let's do a little mini box there. So that's that. And now we know this whole thing, this q dot equals 1, this equals that d over dt term, right? And so if we want to simplify this whole thing down, and we take the integral of some volume integral, it spits out its own volume term. So, as you know, we already canceled out this row term, so I'm just going to go with that. So, basically, this equals 1. All right, why did I do that? Whatever, you get the idea. Cool. So, I'm gonna come back up here. Or that's not, just keep going right here. So, if you multiply this whole thing out, we've got this tank A is 5 feet by 5 feet times some height. So it'll be 25H. So I'll say V volume of A equals 25H1, right? And so now the thing that's changing is this H1. So if we go take the partial, the derivative of it, DH, move this DH over there, dt times 25 equals 1, right? Since the thing that's changing, I just multiplied that d by dt by the h1. A mathematician would get mad at me, but we don't care. So anyway, now this is literally the rate of change of h1 with respect to time. This is what we're finding. So divide the 25 over, right? I'll just do that up here. Get 1 over 25, so let's write over here. Final answer, dh1 dt equals 1 over 25 feet per second, which equals 0.04 feet per second. So that's part A done. And and I think it says like convert it to SI units, whatever, you can do the SI conversion. But there's,
Why did you cancel density in that last step?
because we already did up here, and I just rewrote that whole term, so I just canceled it there too. But yeah, so that's that. Now for part B and C, we just riff off this equation down here the rest of the time. It's the same exact thing. Yeah.
So that just plain q dot, which does that correlate to?
That's this unsteady term from over here.
Okay.
Yeah, because this is the only like weird one where we have to take a weird integral with a changing volume, so I treat it as its own variable for a little bit, and then like these ones are usually this term is your cash money, it'll be like rho VA 99% of the time, unless it's not, which actually on your homework one's not. And come off hours, I'll show you how to do that, but yeah, usually you can simplify that down really nicely. But yeah, this d by dt rho dv, that's what we're gonna be riffing off of for B and C. All right, any like we're pretty much done with all the bid math for this. Any questions on that? The last two parts go pretty quick because it's just the same thing. All right, anyway, if the free surface in tank B is dropping at a rate of 0.2 feet per second, what is the flow rate Q at? It's supposed to be at like 2, but whatever. Okay, so B, we got B, dH2 by dt equals negative 0.2 feet per second. And I say it's negative 0.2 because it's dropping. The rate of change is negative, it's dropping. And so we want to find Q2. Q.2. Okay. So we already said what? At 0.3, it's what? 4? Yeah, 4 feet per second. So same thing. We use this equation down here for Q dot, or would be dH2 dt times area B equals Q dot in minus Q dot out. Right, and this is just This is just that volume integral with all of the stuff already simplified out. This is this equation, this little set of equations and stuff down here. Q dot in minus out, right? And where Q dot is, all that. Cool. So we get negative 0.2, and this is 5 by 8, I think is what it's given. So 40 equals Q dot in. We already said this one coming in is 4, and minus Q dot 2. So just do the math for it really fast. Q dot 2 ends up equaling 12 cubic feet per second. Cool. Like I said, yeah, like it also won't sit in, like this last one won't sit in SI units. Go to unit version if you want. All right, any questions with that? Part C is literally the same thing, but now it's just rising 0.05 feet per second. So I'll go do that one over here really fast. So let's do it. So C. DH2, DT. Okay, so again we have and again, go convert to SI if you want. Go get the conversion. Trust you can do that. But obviously that makes sense because what's coming in is 4 and what's going out is 2. So of course tank has to be rising because that's what concentration mass tells us. What goes in has to come out, and if it doesn't, then that means there's some sort of volume rate of change going on, or that extra mass is being stored somewhere. In this case, it's in the tank. So, and obviously the opposite is true for B. Since way more is leaving than coming in, tank is dropping pretty quick. Any questions with that? Okay, that's crazy. So this, obviously this just used all concentration mass. For this next one, we're gonna use concentration momentum, and that gets a little trickier. Be very, when we get in concentration momentum, be very careful with your sign conventions. Use whatever Castelli tells you to use. As long as you stay consistent with your sign conventions, it's pretty hard to mess them up. Because it doesn't really, at the end of the day, it doesn't really matter what you call your like plus and minus axes, as long as you stay consistent throughout how you use them, you should get the same answer regardless. But I'll get to that in a second. Okay, everybody need any more time with this? Good to go? It's kind of a long recitation. I apologize, but it's important stuff. You'll appreciate it. Okay, here we go. But yeah, I think, whoa, geez, that was crazy. I think on Wednesday you guys will probably learn the energy equation, and you really don't use it that much in here. You use it a lot in thermo class, but this ain't thermo class, so whatever. I don't think it'll be on an exam. I don't think so. Could be wrong. I've been wrong many times before on previous exams, but hey. Just write it down in your cheat sheet. Okay. Yeah, and here's all the key stuff. And they did a little different. They just used straight up M dot for it. I like using the row Q dot. I feel like that's a little better for the scope of this problem. Wait, guys, oh, okay. 2 cubic feet is 0.06 cubic meters. Cool. Okay, here we go. All right, question 2. flow in a circular cross-section pipe is divided into two streams as shown in the figure below. Neglecting the forces of gravity, determine the necessary force to hold the bifurcation. I'll zoom in a little more on this one. Small. Yeah. Sweet. All right. So it's pretty nice. I already made our control volume for us. So I'm just gonna redraw it a little better though. So as you can see, we've got some water coming into this pipe. Then obviously as it gets split by this bifurcation here, it's gonna impart some force on these walls. And we need some sort of reaction force here, like a bolt. You know, we bolt this down. So it provides a little stiffness to keep the thing from bowling away. So that's what we're gonna try to find. We're gonna try to find that force required. And obviously, since everything's just, like, we do have vertical components to these two forces coming down like this, but same exact angle. So those cancel each other out, so we don't care about the vertical force right now. But as I'm sure you can imagine, these can get pretty tricky pretty quick if you have like a different velocity coming out of the bottom one, plus a different angle, and yeah, it gets complicated quick. But this is a nice one, everything's all the same. But there are pressure terms, so we will, like sometimes you can ignore that that pressure term at the very end of that equation if we use like H pressures everywhere. But in this case, we're going to use pressures. And that's pretty much worst case scenario. Just having to carry those pressure terms around. But, okay, so let's start off with our assumptions. And on your homework and stuff, please be very explicit with what assumptions you make. And make as many as you can. I'll see some people they'll put like 10 different assumptions. Like, you don't need to do that, but do my best. Write down everything you can. Okay, so again, we've got incompressible. And I was like writing, that means rho is constant, density is constant. Let's see, this is steady flow. We've got steady flow, so that time derivative term can go away, which is always sweet. And we know this is steady flow because there's no like time velocity gradient coming in or anything, and the control volume's not changing at all. So actually, I forgot to mention that in the last one. When you do pick control volumes, you always, it's just rule of thumb, always try and pick a control volume that is not changing. Like in that last one, we had to pick one that was changing, just because that's like what the problem one is to do. But usually, you know, you have the option to pick whatever control volume you damn well please. So try and pick one that is not changing with time, so you can call that time derivative term 0. It'll make your life so much easier. Anyway, okay, so again, and we're still in viscid, still no friction force, which is really important for this one, because obviously if there is an additional force due to friction, we'd have to account for that. You guys don't want to do that yet. You'll learn how to do that, I think, for exam 3. It's not that hard, there's different equations for it, or empirical equations at least. So. And then the last one I'll put is still 1D fluxes. And do they call it, have you heard that term? Do they still call it that, like 1D fluxes, or do they call it something else? Because that's how I learned to call it. Where the flux is one-dimensional, it's just straight in. There's no angle, whatever. That's what it is. If you want to know, if you want to call it that, go impress your professor or something. Cool, so that's the big ones. And then I'm not going to put no gravity because they give that to us, so that's not really an assumption, it's just something that's given. Okay. But now, and for the rest of this problem, I'm gonna call this like V1, P1, A1, and I'm not gonna call it S. S, what is S? It's an A, it's area. Let's call it area. Okay. So V1 equals 10 meters per second. P1 equals, I'll say 1 times 10 to the 6th pascals. And A1 equals 1 square meter. And then I'll just call this, since they're both exactly the same, I'll call them like A23, P23, V23. Same thing. Equals 0R. Oh, we don't know those, yeah. No, find that. Equals. Why not? Oh, that's a stupid way to write that. And then area. Okay, so now, when you're doing these problems, you kind of have a hierarchy of equations to use. So first, straight up, step one, 99% of the time, is using conservation of mass. And this is kind of an easy one to look at and tell that, because there's only so many terms in conservation of mass. There's like area, density, and velocity, pretty much, in the conservation of mass equation. And out of all this stuff, what don't we have right now? We don't have the exit velocity. So we're gonna need to solve that. And another dead giveaway is if they give you some set of parameters for like an inlet, you know, we've got 3 of them here, and they only give you 2 on the way out, you're probably gonna have to find that third one. It's probably what you're gonna be solving for. And so in this case, it's super easy. We're gonna have to, you just know off the bat, you're gonna have to solve for velocity. So let's do that. So I'm just gonna kind of like do a little box here. So I'll say step 1. Conservation of mass for V23. Cool. So let's go again. 0 equals, I will rewrite this whole thing so you can see how I simplify it. Okay, in the sense, all right, so it's steady flow. So this is pretty sweet. You can just cross this whole term off. Since the time derivative is 0, 0 multiplied by n is 0. So keep going. So now bring this down. And we have 0 equals this whole term, since the areas are all constant and everything, and the densities are constant, and the velocities are constant, this whole thing, this whole term for whatever area you're looking at will just be rho times velocity times area. All right? So let's see, coming in, we've got our normal vector pointing out. So this first one will be negative. So it'll be negative rho v1 a1, right? And now coming out, we have plus rho v23 a23 up here. And for the bottom one, it's the same thing. I'm gonna combine them into one thing in a second, but whatever. Rho v23 a23. Right. And like I said, we don't care about like the components of these because the normal vector is also at that same angle. So if you want to carry a sine theta term around, that'll just cancel itself out at the end. Go for it. If you really love angles, but whatever. So I'm just gonna factor these out right away. So we get v1 a1 equals 2 v23 a23. So we've got 10 times 1 equals, let's see, we've got 2 times v23 times 0.4. So solve for v23, obviously. v23 equals, I think it's 12 and a half. Yeah, 12.5 meters per second. All right, so there's step 1. So, found that out, nice. And I guess that could be another assumption you could make too, that like the parameters at 2 equals the parameters at 3. You could also say that, but it's kind of evident, kind of self-explanatory. Okay, so there's step 1. Now we move on to conservation of momentum, which is the trickier of the two, but it's still go pretty quick. So we get, I'll do it right here. So I'll rewrite the whole thing. So the external forces equals it's funny, this takes you a surprisingly short amount of time to memorize. Like in a little bit you like won't even think about it. You just do it. Alright, so here's the whole thing. So like before, we can cancel that, okay? And now, right away, I'm just going to break everything into its x components, right? Where this theta equals 30 degrees, right? Obviously, it's the same angle for both, right? So, I'll say break into x components. Okay. And also, if you're particularly astute and on the ball, you'll see that this CS term here is the same exact rho VA, but just with an additional velocity term. So it'll just be rho V squared A. And then obviously times like sine theta, or cosine theta in this case. So we're gonna do that. So, and like I said, it doesn't, for right now, you know, sure, we're gonna find our coordinates, like, you know, x, y, whatever. But for finding this f of x, this x force, it doesn't really matter what direction you call it, because you know intuitively what direction it's supposed to be going anyway. So if you end up getting like a negative number, just say, hey, it's this magnitude going left. It's like, whatever. It just means you assumed a direction. If you assumed your axis to be in the wrong direction, you'll live, trust me. Okay, so let's break this into x direction. So we've got fx equals, coming in, right? Coming in, we still have that negative rho. Oh, and for this, we will have to carry the density term with, because obviously the pressure doesn't have a density term, so we can't just factor it out. So let's go. Coming in, we've got rho v1 squared a1. Now coming out, we have plus, I'll just do 2, I'll do that same thing, 2, like v23 squared a23. 2 v23 squared a23 cosine theta, right? And now for our pressure terms. The pressure terms can get really tricky really fast, but don't worry about it. For my sign convention, I'm going to call this pressure force plus, and then these ones minus. And I think about that more like in the direction I have the stuff written, what way is that pressure force pushing? It's pushing positive x. So that's the way I write it. Sometimes you'll see the pressure term written just over here to account for some other sign convention stuff. Whatever, just know it's the same thing. So we've got plus P1A1, then minus 2P23 A23, still cosine theta. All right, still at that same angle. So now we're ready to solve. We actually know everything about this. The only thing we don't know is this, which I've already isolated literally. It's just a plug and chug situation now. So go plug everything in. I'll say everything is known. Everything's known, go and plug in your values. So let's do that really fast. This should be, this is actually a pretty good number, so I'll just write it up here. You end up getting, it's like 506.7, yeah. It's 506.7 kilonewtons, or 506.7 times 10 to the 3 newtons. Yeah.
So we don't have the density at 2 and 3?
Yeah, we do. Yeah. Oh, I just didn't write it.
Okay.
Yeah, that's my bad. Yeah, is that what your same question was?
No, I was wondering, why did you say the pressure at P1A1, why is that positive?
Because that's how I define my coordinate axes. If you look at it like a force term,
Oh, it's good.
pushing in the positive. That's, like I said, the sign convention can get really confusing. Whatever, if Casper said to use a different sign convention, be my guest. I think it's nice to like see different ways of going about doing these, because really, there are kind of an infinite number of ways to go about solving these, because you can pick whatever control volume you want. If you wanted to have a control volume that encompasses like this whole entire thing, you use it, like it'd be more complicated, you could, you know. So, yeah, whatever sign convention you want to use, whatever sign convention you get comfortable using is more important, all right? I always hate when people say, oh, do these problems in this way, like, dude, since there's so many ways of doing these, whatever one you're comfortable with, if you get the right answer, obviously you know what you're doing. Just get comfortable with the concepts and know why you're doing what you're doing. And you'll end up doing really well. Yeah, good catch. Yeah, I just forgot to write that extra Tennessee term. Yeah. Cool. And obviously there's no density term, the pressure forces, that's independent of material density. So.
How are we able to equate our FX to the conservation of momentum? How do we?
Because all of those
It's the
terms,
sum, it's the sum.
yeah, all of those terms end up being pressures if you do the dimensional analysis for it. If you wanna go back to week 1, do some dimensional analysis, go for it. Yeah, trust me. Like I said, this is all from like Reynolds transport theorem stuff, where like you get everything. There's like a really general form for it. And it's actually kind of interesting. But yeah, everything ends up working out to be forces. Because like you can see that from the pressure term, you get P times A, which is a force. And so it just kind of tracks from there. Anyway, okay. Anything else? Cool. All right. Well, yeah, this stuff's important. So if you're confused, like if you're really stuck, you're embarrassed to ask in front of a class, shoot me an email. We can work something out. But yeah, this stuff's important. So if you do have questions, like really, let me know.